Consider the following polynomial function. And here we are given f of x is equal to minus x minus 2 times x plus 1 squared times x minus 1 squared. Now here we're being asked to identify the end behavior of the graph, to then find the zeros and their multiplicity, then to use this multiplicity to describe the graph's behavior at each zero. We're also asked to find the y-intercept and to sketch the graph. So part A, we want to identify the end behavior of the graph. So we need to apply the leading term test. So in order to apply this leading term test, we need to identify the leading term. So recall that for a generalized polynomial, our leading term is a sub n, our leading coefficient, multiplied by x to the n. And this is where n is the largest degree of the polynomial. So how are we going to identify this leading term given this factored polynomial? Well, we could expand everything out, but that's going to take a long time. So what else can we do? Well, let's begin by noticing we have a negative 1 in the front. So that's going to be our a sub n. But still, how do we identify x to the n? Well, let's think about each one of these binomials. So with our first binomial here, notice that we just have a single x. Now with this second binomial, it's a binomial product, right? So that's actually x plus 1 times x plus 1. So if we were going to expand that out, the first term would be x squared. And I'll leave the rest of the math to you. Now moving on to our third term here, again, it's a binomial product. So that's actually x minus 1 times x minus 1. And if we were to multiply that out, we know that x times x is again producing x squared. So by thinking about it like this, we can actually see the total number of x's in this function without having to do all of that multiplication. So we're ready to identify our leading term. We can say that our leading term, a sub n times x to the n, is going to be negative 1 multiplied by x times x squared times x squared. And we can use our exponential addition here to see that our leading term is negative 1 times x to the 5th. Woohoo! So now we're ready to apply the test. So we can say that our leading coefficient, a sub n, is negative 1, which is less than 0. And our degree is 5, which is an odd number. So therefore, since our leading coefficient is negative and we have an odd degree, this is letting us know that the left-hand side of the graph points up and the right-hand side of the graph will point down. Beautiful. So this is the end behavior of our graph by our leading term test. Now, in part B, we are asked to find the multiplicity, find the zeros, and identify the multiplicity of all of our zeros. So in order to find the zeros, we need to set that function f of x equal to 0 and solve for x. So here we go. We have minus x minus 2 multiplied by x plus 1 squared multiplied by x minus 1 squared is equal to 0. Now notice again, out in front we have that negative 1 coefficient. Let's get rid of it. So we're going to immediately simplify by dividing both sides of the equation by negative 1. So we see negative 1 divided by negative 1 cancels itself out to 1, leaving us with just these binomials. We have x minus 2 multiplied by x plus 1 squared multiplied by x minus 1 squared is equal to 0. And so we can now think about each one of these binomials separately. So we have the case where x minus 2 is equal to 0. We have the case where x plus 1 squared is equal to 0. And then last but not least, we have the case where x minus 1 squared is equal to 0. So here we go, solving each case. Case number 1, to isolate x, we are going to add 2 to both sides of the equation. So minus 2 plus 2 cancels itself out to 0. And we see our first 0 is x equals 2. Woohoo! In case 2, we see that the x is trapped by the square. So we need to take the square root of both sides of the equation. So this is leaving us with x plus 1 is equal to 0. And solving for x, we need to subtract 1 from both sides here. So 1 minus 1 cancels itself out to 0. And we can see our second 0 is x equals negative 1. And last but not least, with case 3, again, we see that the x is trapped by the square. So to remove that square, we will take the square root of both sides. So we are left here with x minus 1 is equal to 0. And to isolate x, we are now going to add 1 to both sides of our equation. So minus 1 plus 1 cancels itself out to 0, leaving us with x is equal to 1. So there you have it. These are our zeros. So we can say that therefore, the zeros of this beautiful polynomial function occur at x equals negative 1, x equals positive 1, and x equals 2. Now remember, these zeros are also the x-intercepts. So we could equivalently write them in their ordered pair form, negative 1, 0, 1, 0, and 2, 0. So we'll keep those ordered pairs in mind because in part D, we need to sketch a graph. But first, before we can sketch a graph, we need to think about the multiplicity of each one of these zeros and how it's going to affect the behavior of the graph at the x-axis. So giving ourselves plenty of room here, we want to begin by thinking about that reduced polynomial. So we had x minus 2 multiplied by x plus 1 squared multiplied by x minus 1 squared is equal to 0. So again, in order to classify this multiplicity, we need to think about each one of the factors that's going to appear here. And we also need to think about how many times they appear. Once we have the factors and the total number of times that each factor appears, then we'll be able to make our multiplicity conclusions. So here we go. We can see, looking at this beautiful polynomial function here, that we have 3 factors. We have the factor x minus 2, we have the factor x plus 1, and we also have the factor x minus 1. So looking again at this polynomial function, how many times does the factor x minus 2 appear? Once. So since this factor appears 1 time, this means that this factor has a multiplicity of 1. Which will make a love note to ourselves that this is an odd multiplicity. Now, how many times does the factor x plus 1 appear? Twice. It appears 2 times in the polynomial function above, which means that it has a multiplicity of 2. And again, we'll make a love note here to ourselves that this is an even multiplicity. And last but not least, how many times does the factor x minus 1 appear? 2 times. It appears twice. So just like above, this has a multiplicity of 2, which again we know is even. So, based on the multiplicity and whether or not this is odd or even is going to help us determine the graph's behavior at these zeros. So recall that with an odd multiplicity, this tells us that the graph of the function, so the graph of f, crosses the x-axis at this 0. So it crosses the x-axis at the 0, x equals 2. Beautiful! Now, with these last 2 factors, they both have an even multiplicity. So I want you to recall that an even multiplicity tells us that the graph of the function is tangent to the x-axis at these zeros. So the graph of f is tangent to the x-axis at both zeros, x equals a -1, and at x equals +1. So we have officially made our multiplicity conclusions for each one of these zeros. Beautiful! So now we are officially ready to move on to part C, where we're being asked to find the y-intercept. So recall that the y-intercept is where the graph of a function crosses the y-axis. So to find the y-intercept, we are going to set x equal to 0 and solve for y. So since y equals f of x, we can say that y is equal to, we have minus 0 minus 2 multiplied by 0 plus 1 squared multiplied by 0 minus 1 squared. And so we can simplify here and say we have minus a minus 2 multiplied by 1 squared times -1 squared. And so we can see here we have a negative times a negative, which produces a positive value. So this is equal to positive 2. 1 squared is 1. -1 squared is 1, leaving us with 2. Woohoo! And so therefore our y-intercept, or the y-intercept of this beautiful polynomial function, is occurring at the ordered pair 0, 2. So, last but not least, we are now officially ready to take all of this information and use it to sketch the graph. So part D, our last part, is to sketch the graph. So before we begin, let's recall what we just found. Well, we know from part A and the leading term test, we know that the left-hand side of the graph is pointing up and the right-hand side of the graph is pointing down. Now, from our zeros, we know that the graph has 3 x-intercepts, and from the multiplicity of those factors, we know the graph's behavior at these zeros. So we have an x-intercept at the ordered pair, -1, 0, and this had an even multiplicity, so the graph is tangent at this 0. We have a 0 at 1, 0, and again, we had an even multiplicity, meaning the graph is tangent to the x-axis at the 0. And last but not least, we have our third 0 at the ordered pair, 2, 0. Now this factor had an odd multiplicity, so the graph is going to cross the x-axis here. And above, we found the y-intercept. So we'll keep that y-intercept in mind. This is where the graph is crossing the y-axis at the point 0, 2. So we're going to now take all of this information and use it on our sketch. So let's consider the coordinate plane. So the first thing I'm going to do here is plot the zeros, plot those x-intercepts. So we have an x-intercept at -1, 0. We have another x-intercept at 1, 0. And last but not least, we have a third x-intercept at the ordered pair, 2, 0. Now, to help us with our graph, let's keep our multiplicity conclusions in mind. So we'll put a T for tangent next to the factors that have an even multiplicity, and we'll put a C for crossing at those factors that have an odd multiplicity. Now, we also have the y-intercept up here at the ordered pair 0, 2. And now, last but certainly not least, from our leading term test, we know that the left-hand side of the graph is pointing up and that the right-hand side of the graph is pointing down. Now, we already know that we always read a graph starting from the left-hand side and moving to the right-hand side. So, to sketch this graph without having to calculate any other points, we're going to begin over here on the left and connect all of these features with a smooth curve. So here we go. Starting from the left hand, or the most left-hand side, we move down until we hit that first 0. Now, keep in mind, we know the graph is tangent at this 0, so it's going to bounce back up. The graph must cross through that y-intercept, and it must go back down to hit that next 0. And the graph is going to bounce back up because we're tangent to the x-axis at that 0. And somewhere around here, the graph must turn around so that it can go through that final 0 and connect with that right-hand endpoint. And so here we have it. This is a beautiful graph of that polynomial function. F of x is equal to minus x minus 2 multiplied by x plus 1 squared times x minus 1 squared.